All right. You're welcome to the GMAETS 41's live stream class as we kick off our chemistry class this evening. A moment ago, you recall that we treated, physics, where we looked at measurement of heat energy. So we are done with that, and like I told you, just had to take a little break and come back for chemistry. Okay, so we shall be looking at electrolysis. Wipe this from the board so that we kick off straight. So you are welcome once again. If you can hear me, indicate that you can hear me so that after wiping the board, I will kick off with the class right away. So in electrolysis, I want to inform you that I already treated the concept of electrolysis in one of my video lessons, which you can actually search out. Okay, you can reach out for the lesson. Just slide through the GMAETS 41's playlists, and you will see the lesson on electrolysis, where I actually interpreted the concept of the laws of electrolysis, Faraday, and the Faraday's first and second laws of electrolysis. So we have here electrolysis. In fact, we refer to this as electrochemistry. Okay, this part of chemistry, refer to it as electrochemistry. So thank you very much for welcoming me back. Now we are going to kick off, like I said, right away. So there will be no much background given here because, like I said, I have a video lesson dedicated to electrolysis, where I define what electrolysis is as chemical decomposition of a compound, either in its aqueous or molten form, by passing current through it. I've already treated that. And then, of course, in that video lesson, I talked about the concept of the anode and the cathode, which are terminals through which current can enter and leave an electrolyte. Define what an electrolyte is as an aqueous solution or a compound in molten form that can conduct electricity, can allow current to flow through it. Because it's in liquid form or molten form. That liquid form is the aqueous form, which is chemical liquid, okay? Then, like I said, anode and cathode, they are terminals through which current can enter and leave an electrolyte. So you want to take that video lesson, okay? You want to take it. It's not a live class. Like I told you, on this platform, we have both live classes and we have that which is pre-recorded, which you can take anywhere, anytime, any day. It doesn't require you to be at that point, to be live at the time that I made that video. So without wasting time, we are going to move on straight to what we've got here. All right, like I said, the anode is a terminal through which current enters the electrolyte. And because the anode is a terminal through which current enters the electrolyte, since current and the electron, they move in different directions, it means that the anode is a terminal through which current leaves the electrolyte. You want to take note of that. Then cathode is the terminal through which current leaves the electrolyte. Cathode is a terminal through which current does what? Leaves the electrolyte. And so that means that cathode is the electrode through which electrons will enter the electrolyte. Remember, like I said, it is because electrolytes, the electrodes, right? Or electrons, rather, I mean to say, electrons and current, they move in opposite direction. So if anode allows current to enter, anode will allow electrons to leave the electrolyte. Now, if cathode allows current to leave the electrolyte, It means that cathode will allow electrons to enter the electrolyte. You want to watch out for something like that, the examiner can test you on it. So now, when you deal with this aspect of chemistry, we have that which we call electrolytic cell, and we have that which we call electrochemical cell. I talked about this concept in that video lesson, and I really encourage you to take that lesson. Are you following, right? It shouldn't be all about live class. I have class that is not also live, pre-recorded. Electrolytic cell, electrochemical cell. Can learn much about them. This electrochemical cell is also known as voltaic or galvanic cell. All right. Now, why I decided to make reference to these guys is because of the concept of anode and cathode quickly, which are the two electrodes you see either in electrolytic cell or electrochemical cell, right? So, hey Barry, which country, sir? This is from Nigeria, okay? This is from Nigeria. Now, in electrolytic cell and electrochemical cell, you have anode, you have cathode. The only thing is that in electrolytic cell, the anode is positive and the cathode is negative. But in electrochemical cell, the anode is negative and the cathode is positive in electrochemical cell. So you want to take note of that. And well, the reaction that takes place in both cells are the same thing, right? The reaction that takes place in both cells. What do I mean by that? In terms of the reaction that takes place in the half cell, in the cathode and the anode, they are the same. For example, in electrolytic cell, reduction takes place in the cathode. In electrochemical cell, reduction also takes place in the cathode. And that reduction has to do with gain of electrons. And then at the anode, oxidation takes place, whether anode of electrolytic cell or anode of electrochemical cell. You want to take note of that. Oxidation takes place in the anode. Like I said, the only difference is that anode in the electrolytic cell is positive, cathode is negative. The electrochemical cell, also called voltaic or galvanic cell, anode is negative and cathode is positive. That's just the major difference in terms of the electrodes. Then take note, in electrolytic cell, what takes place there is electrolysis, where you use current to decompose a molten compound or an aqueous solution. Pass current through it and that solution will decompose. But in electrochemical cell, you produce current by making use of chemical changes. Chemical changes are converted into current production. Whereas in electrolytic cell, current effect is used to decompose the chemical content, the electrolyte that is being used there. I think these are just little of the things I want to talk about a little. You can learn more by sliding through to the GMAETS 41's playlists. Visit our Chem 101 playlist, right? Chemistry playlist, and you would see the concept of electrolysis. There I dealt with Faraday's first and second laws of electrolysis, which of course you are going to meet in this class. So you want to be well prepared about it. You know, Faraday's first law tells us that the mass deposited during electrolysis is directly proportional to the quantity of electricity that passes through the electrolyte. Mass deposited directly proportional to what? Quantity of electricity. And quantity of electricity is IT. We use Q for quantity of electricity and it's equal to IT. Then you want to remember that 1 Faraday, the quantity of electricity at 1 Faraday is equal to 96,500 coulomb. Memorize that. Are you following? Although in any given question, that constant should be given to you if it is required. Then Faraday's second law of electrolysis tells us that if you pass the same quantity of electricity through solutions of different electrolytes, that the moles that is going to be produced will be inversely proportional to the charge of the ion of that element, of that solution. the moles produced, the relative amount of the substances that will be produced if you pass the same quantity of electricity through this different electrolyte. The moles produced will be inversely proportional to the charge on the ion of that metal in that case, right? Let us assume that these two guys are two different solutions and you pass the same quantity of electricity through them. The relative number of moles of this black marker that will be deposited, the relative number of moles of this blue marker that will be deposited will be inversely proportional to their charges. So if this one, the charge is maybe, let's say 3 plus, and the charge of this, the valence, let's say, is 1 plus, then it means that the moles of each of them deposited will be inverse, which means the one that has a higher valency will deposit, you know, the mass of it, the number of mole of that one that will be deposited will be small. And this one that has lesser ionic charge, lesser valency, the moles of it deposited or the mass of it deposited produced will be higher. That's the meaning of Faraday's second law of electrolysis. So it is time now. We are going to move on to the questions that have been dropped by GMAETS 41. I think GMAETS 41's jump and white student, group 9. Group 9, they are the ones that dropped this question, and we are going to move on straight with our first question, no time. Okay? We want to learn more about the basic concept of electrolysis, factors that affect preferential discharge of a particular ion on a cathode, on an electrode. The factors, there are 3 factors: the position of that ion in the electrochemical series, the nature of the electrode, and the concentration of the solution. These are the 3 factors that affect, you know, what to be deposited or what to be discharged on the electrode. That video lesson will explain that. Our first question here, Q1, right? Question 1. I'm going to copy it on the board. During electrolysis, (2.0 grams). Let me see the space so that, okay, so I think I can still write this. 2.0 kilogram. I mean, 2.0 gram, rather, not kilogram, of a metal is deposited using a current of a metal is deposited using a current of 0.5 ampere in 3 seconds. In 3 hours, that's what I have here. The mass of the same metal which can be deposited using a current of 1.5 ampere, the mass of the same metal which can be deposited using a current of 1.5 ampere in 1 hour is, so we don't know, we have the options here. Option A is 1.0 gram, option A is 1.0 gram, option B 0.5 gram, option C 3.0 gram, option D 2.0 gram. So let us look at the question. During electrolysis, 2.0 gram of a metal is deposited using a current of 0.5 ampere in 3 hours. The mass of the same metal which can be deposited using a current of 1.5 ampere in 1 hour is, this question is interesting, you know, it's interesting and scary, because you know what? I have not solved a question of this particular kind before. Or this particular type, I've not. But like I said, dear friends, you know, this is GMAETS 41, right? I believe in one thing, and that is what science should be. Science, mathematics, engineering, technology, it's about critical thinking. That is what is really driving the world now. You talk about STEM, science, technology, engineering, and maths. Are you following, right? You work with the knowledge of the known, because you must always move from what you know to what you don't know. And I put it to you, as long as you know something and what you don't know has one, even if it is an insignificant relationship to what you know, you can actually use the knowledge of the known, expound on it, and actually get the unknown. How did we come about all these plenty inventions in scientific and technological world? It's based on using knowledge of the known, make certain assumptions, and you arrive at something. You can try and fail sometimes, but eventually you may arrive at something unique. That is the spirit. So let us deal with this question. I'm just looking at this. See, problem number one is that we don't even know the metal. If we know the metal, we could have gotten the valency and then determine the number of Faradays required. Are you following, for that metal? But we don't know the metal, and that is what makes this question very, very tough. But hey, I've looked at it, and it's 1 + 1 to me. It's 1 + 1, because I've known where the problem came from. And I've just told you, we don't know the metal. If we had known the metal, we could have established the Faraday, the number of Faraday, which is equivalent to a given quantity of electricity that would have deposited this particular mass. So what we're going to do is to find what that metal is. And I might not be interested in getting exactly the name of the metal. What I'll be interested in is the number of Faraday that would deposit the relative atomic mass of that metal. Okay? So let's see. During electrolysis, 2.0 gram of a metal is deposited using a current of 0.5 ampere in 3 hours. So this is what we're going to do. Let me assume I don't know the metal. I'm using X to represent the metal. And then let me say that it will receive n number of electrons. I don't know. Now let this be n ion, right? You know, just like you have 2 plus, 3 plus. Let me say this is n plus. I don't know the valency of that metal. Whatever the valency is, which I'm using n here, is going to receive n electron and then be deposited as a metal. Right? So here I'm going to say n Faraday will produce the relative atomic mass of the guy I do not know. But from the question, we are told this 0.5 and this time, this current and the time can be used to calculate the quantity of electricity that was used to deposit this guy. If you look at this, they said during electrolysis, 2 grams of a metal is deposited using this quantity of electricity. I've told you already that quantity of electricity is equal to IT. I mentioned it in just a brief summary to this guy before I started. So I can say that, okay, we know that, what is it, IT, right? We know that IT, which is IT, current times time. Please permit me to now write it 0.5 times 3 times 3,600. Why did I multiply by 3,600? Current, which is I, times time. This time is in hour, so you multiply by 3,600 to convert to seconds. But it doesn't matter because this one is also in hour, so it will also convert to second. But please, let me do the right thing. What do I mean by the right thing? I could solve this without converting to second, no problem. But let me not just go straight on without letting you know that it is necessary for you to convert in most questions. But in this particular question, since this guy is in hour, this is in hour, there is no need. So this is going to give us the mass deposited is 2 gram or 2.0 gram. So you see, with this stuff, one can now say that, okay, fine. If this quantity of electricity deposited this, coming over to this, we are now asked the mass of the same metal. Since it is the same metal, right? This same thing will hold. This same thing will still happen. That is to say, the number of Faraday required to discharge the relative atomic mass of that element will still be the same, because it is the same metal that you are dealing with. And if that is the case, I can simply bring this guy down and then formulate a direct proportional relationship. So it implies that this quantity of electricity, which is this times this, 1.5, another IT, let this be I1T1. Then the next I1T2, I2T2, which is 1.5 times 1 hour. 1 hour is 1 times 3,600 seconds. will not deposit which mass you don't know. So eventually this question, you know, I wasted time in this question because, to be honest, this is my first time of meeting this stuff. And the truth is, it's not as if there is a special time I give to this stuff. I like appearing real. If we meet a question and I cannot break it down, if we meet a question and I cannot analyze it, it is expected I will move on to the next question. No two ways about it. Yeah, I'm not here to play prank on anybody. All right, that is the challenge or the problem some students have, thinking that once they enter exam hall, they must solve all the questions. A question that does not make sense to you. You've not met such question before, and you cannot analyze it per se. You've got no choice. That's why you are told, move on, don't waste your time. But you know, because I am teaching and I feel that I can analyze this, you know, this is a teaching time. But I've not seen a question like this before, to be honest. I didn't take my time to say I solved this before now. No, I want to be real to you guys. If I didn't have any idea on what to do here, I could have told you, let's leave it and move on. You could see some question which, if I saw, I'll tell you, okay, this is what I feel like. Okay, this is my answer based on so reasons. I think we've met up to like 3 of such questions since I kicked off this live classes fully. And I tell you, if you think otherwise, provide your own answer. Then let's reason it out and see. That is the scientific process, right? So because it is the same metal, it means all I have to do is, okay, fine, if this quantity of electricity deposited this mass, therefore, this quantity of electricity will deposit what? We're not going to cross multiply, but before cross multiplying, remember, this guy and this guy will cancel out. They'll cancel out. Then if you cross multiply, 0.5 times 3, then times m, will give you 0.5 times 3 times m. Let me show you this way. And then 1.5 times 1 times 2. Let me still punish myself to show it. You don't need to overwaste time in exam hall for this. So from here, to get the mass deposited, is going to be 1.5 times 2. And 1.5 times 2 is equal to what? You can find it out. That's going to be equal to 3, right? So it's going to be 3, this guy, divided by the coefficient of what you are looking for, which is 0.5 times 3. 0.5 times 3. Let me put it this way. Now, 3 all over 0.5 times 3. You see, if I had actually met a question like this, I wouldn't have stressed myself to do this. I've just gone straight to tell you that this question uses direct proportion. But I had to figure it out, think it through, analyze it based on the knowledge of the note. See, I'm doing this to encourage you guys. Don't just easily give up on something, and don't look at something and think it is beyond your doing. God is giving us the capacity. Yes, the brain there is a great wonder. And God and Helper Jehovah has given this to us free of charge to make use of it. So you do make use of this thing. Are you following, right? Make use of it. Look at the question, analyze it based on what you previously know. All right, if I'm in exam hall, what I'll do is just divide this 1, divide this 1. Then 1 over 0.5 is the same as 1 over 2. That over 2 will go up, and the mass will be 2 grams. How come? Why are they the same? Why are they the same? Okay. This is funny. Or is it not funny? Let me check why they might be the same. 0.5 times 3. Okay, good. 0.5 times 3 is 1.5. So do you see? This is actually 1.5 times 3,600. This one is also 1. Very funny question. So do you see clearly? And it is good we've analyzed it so that you can see what is in this question. The correct answer is still the same thing. But it's good. Now work on it for you to see it clearly. But if I wake up and say this question is like, don't worry, it's the same thing. You might just be looking at it, how? And that is good. That's the GMAETS for the ones effect. All right, so we are done with this question. And of course, you heard the option earlier. Option A is 1.0 gram. B is 0.5 gram. C is 3.0 gram. Then D is 2.0 gram. So the correct answer is D. 2.0 gram. So at least if you meet something like this in exam hall, you know what to do directly. Because in the exam hall, that is not a time for you to start thinking, how is this question being solved? It is a time to attack. That's why you are going through all this coaching. So once you're in exam hall, you already know what to do. Oh my gosh, we wasted a whole lot of time on this question, but it's not my fault. I told you that it's not as if I have a pre-knowledge of this before now. So we are in real-time exam situation, a case. So we move on to the next question. This is not calculation. It is not calculation. So I'm going to dictate it and then we answer straight on. In Faraday's law of electrolysis, a graph of the mass deposited, against the quantity of electricity is plotted. In Faraday's law of electrolysis, a graph of the mass deposited, a graph of the mass deposited against the quantity of electricity is plotted. The slope of the graph gives option A, the energy released. I don't think so. Option B, the electrochemical equivalence. The plotted mass against quantity of electricity. I'm suspecting that. Option C, the current flow. Option D, the charge released. Now, I'm looking at this, that the correct option is B, the electrochemical equivalent. All right? I'm sorry I didn't talk about that in the background introduction to this, but I guess in that video lesson on electrolysis, I highlighted that. In our physical jam class, jam and wire class, I also talked about that. See, from Faraday's first law of electrolysis, we have that mass is directly proportional to quantity of electricity. So it implies that mass is equal to, we use Z as the constant of proportionality. That Z is called electrochemical equivalence, ECE, electrochemical equivalence. So if you plot a graph of this against this, if you plot a graph of M against quantity of electricity, something of this kind, mass against quantity of electricity, and quantity of electricity is equal to IT, you know that already. Please, I showed it here. You are going to get a straight line graph that likely will pass through the origin. Now, the slope of the graph will be equal to Z, which is electrochemical equivalent. Electrochemical equivalence. Good. That is what is known for this guy. That Z there is the slope. In a normal graphical work, if you have plot y against y against x, the slope is what is multiplying x. Let me assume I give you this equation of a straight line, y equal to 3x plus 5. You are plotting y against x. The slope is this number multiplying x. So here, if I plot m against q, the slope, which we call the electrochemical equivalence, in some cases we use E for that guy. It doesn't matter, you can use any alphabet for the electrochemical equivalence. That is the slope of the graph. So the correct option from the options provided here is option B, like I said. Option B is correct. Option B is correct. We are moving on to the next question, number 3. And I hope that this has not cut off from your view. Let me take a look. All right, that's good. It's showing. It's showing. It's showing. All right, someone had just asked which grade is this. Now the truth is, at O level, this is a work for grade 8, right now? Grade 8, 9, grade 11, which we call SS2 in Nigeria here, right? Which we call SS2 in Nigeria. However, it's interesting to know that this is also advanced chemistry. Yeah. Why do I call it advanced chemistry? It's done by people in advanced level in electrochemistry. I have warned you guys. It shouldn't be all about which grade, which level, which grade. I think your question should be, which topic is this? Then once you know the topic, ask yourself, am I offering a course that contains this topic? That should be your interest. Because if you are offering a course that contains this topic, definitely there is nothing else you are learning that is completely different from this information or background information of that topic. So take note of that. Let us move on to our next question. That's question number 3. Question 3. The electrochemical equivalence of silver is 0.0012 gram per coulomb. Let me copy that on the board. The electrochemical equivalence of silver is 0.0012 gram per coulomb. If 36.0 gram of silver is to be deposited, by electrolysis. Please, my gen is about going off. So just give me a moment quickly. I'll be back so that at least I have a reserve of petrol. Let me top it up quickly. I'll be back. All right, so I'm back again. I'm sorry for the little breakthrough. So the little break rather. Excuse me. So you see, it's not easy, right? So I was copying a question on the board. Please, if you can hear me, let me know because I try to control background sound a bit. I have to put off the mic. If you can hear me, please indicate that you can hear so that I would continue the class. Thank you very much, Promise, for appreciating my effort. All right, Mary, thank you for indicating that you can hear. So we continue with the question. So where are we? The electrochemical equivalent of silver is 0.0012 gram per coulomb. If 36.0 gram of silver is to be deposited by electrolysis on a surface, on a surface by passing a steady current I don't even know, copying the question on the board and just dictating which one seems to be faster. You can tell me about that so that we work and conserve time. Passing a steady current for 5 minutes. The current must be so we don't know. All right, so that's the question. The electrochemical equivalence of silver is 0.0012 gram per coulomb. If 36.0 gram of silver is to be deposited by electrolysis on a surface by passing a steady current for 5 minutes, the current must be, we do not know. So this is just a simple question. The options provided, we have option A, 6,000 ampere. Option B, we have 100 ampere. Option C, 10 ampere. Option D, 1 ampere. Solving this is simply to recall that mass deposited is equal to ZQ. And that ZQ is also equal to ZIT because Q is equal to IT. So this mass is equal to ZIT. We are given the electrochemical equivalence, we are given the time. The time is 5 minutes. We shall convert it to second by multiplying it by 60. And so we have to look for the current. So current is simply equal to mass divided by what? The electrochemical equivalence times time. So this is just the formula I use in solving it directly. What is the mass? The mass given to us in the question is 36. Now, under electrolysis, please take note. You do not convert the mass to kilogram. You don't. You solve in the unit of gram. Are you getting me right? You solve in the unit of what? Gram. So you want to bear that in mind. So divide this by our electrochemical equivalence, which is 0.0012, then multiply by time. And the time is 5 minutes. You're going to multiply that 5 minutes by 60 to convert to seconds, okay? To convert to seconds. So you can multiply this out. Sorry, I've got to reach out for my calculator, right? But one can still work on this if you want. This will give you 300, and then you reduce it. But no time, please. I know time. No time. So let us move on. So what we have here is 36 divided by, to press the denominator, I open up a bracket, 0.0012, then multiply by, I think 5 times 60 is 300. So let's see what we've got here. This is 100. So the current is going to be 100 ampere. And of course, that's the current that is required to deposit this mass, 36 gram. The correct option from that provided for us is going to be option B. So option B is the correct option, okay? And we are moving on. The next question, no time. I say no time, no time. Do we have time? We have to round off so we can go and rest. Myself, I have to sleep because I have physical German white lesson class to hold tomorrow morning. Okay, so our next question as provided. Question number 4, right? Question 4. The quantity of electricity required I can write fast, you know, but I'm still worried to find out which one will be better, dictating or trying to write fast on the board. The quantity of electricity required to deposit 180 grams of silver. The silver was written as Ag. So it's expected you know the chemical symbol of silver. From a molten silver nitrate. From a molten silver trioxo nitrate 5. Silver trioxo nitrate 5 is, so we don't know. In brackets, silver, the relative atomic mass is 108. Then we now have the options. The options: A, 1.08 F. B, 3.30 F. C, 1.67 F. D, 1.80 F. I guess that F there represents a likely number of Faraday. Okay, number of Faraday. The quantity of electricity required to deposit 180 grams of silver from a molten silver trioxo nitrate 5 is. Now, I would like to say this quickly. You can use the formula directly to solve this guy. I'll give you that formula right in the exam hall, but that is after I would have shown you something. Here we know the name of the element. The element is silver. The name was given. The element is what? Silver. And because the element is silver, the name was given to us. It simply means that we know the valency of that guy. We know the valency of that guy. Am I communicating? The valency of silver is 1 plus, which gives us the number of Faraday in standard. 1 Faraday will deposit this relative atomic mass. So normally, if you said, okay, you want to show how work, you should have Ag plus. It will collect 1 electron from the cathode and then be deposited as silver metal. This is in aqueous form, AQ. This is also aqueous. So looking at what we have here, right? Finish up with that part of the board because I'm going to wipe that left part. I'm going to wipe that left part. Chiagozi Andrew, sir, please repeat. What am I repeating? Okay, Favor Chichuku, dictating is better, all right? Okay, that's good. So I'm going to do that next. Chiagozi, you're saying I should repeat. I don't know what I am to repeat. If any one of you have any question to ask, please be specific. Let me know what you are requesting for. Okay, so below this half-cell reaction equation, this is a reaction equation taking place, right, at the anode, at the cathode rather of the electrolytic cell. Just below it, what we have found out is that 1 Faraday is equal to 1 Faraday will produce the relative atomic mass of that guy. 1 Faraday is equal to relative atomic mass of silver in that case. Are you following, right? And 1 Faraday is 96,500 coulomb. 96,000, let me put it here. 1 Faraday, which is equal to 96,500 coulomb, will produce the relative atomic mass of silver. And the relative atomic mass of silver, let me write this clearly, equal to RAM of silver. Relative atomic mass of silver was given to us. The implication here is that 96,500 coulomb would give us what? Would give us 108 gram. Now, from the option given to us, they gave us the value in terms of number of Faraday. So there is no need even using this. There is no need using the 96,500. We can use this one directly. So let me still indicate 1 Faraday, which is equivalent to 96,500 coulomb quantity of electricity will deposit this. Therefore, how many Faraday? Can I say that, which is the quantity of electricity now, will produce the mass given to us, which is 180 grams. So this thing is simple, right? From the reaction equation and the standard, we know that 1 Faraday, which is 96,500 coulomb, will deposit 108 gram mass of silver. Therefore, what quantity of electricity will now deposit 180 gram of silver? Look at it. 1 Faraday gave us this. So what quantity will now give us this one? You have the choice of using this 96,500 Coulomb to calculate, or use this Faraday to calculate. It all depends on what was given to you by your examiner. In this case, in the options, I read out the options for you guys, right? In the options, what we have, they were given in terms of Faraday. You have this Faraday, the other Faraday. Are you getting me right in terms of the value? Therefore, I am going to make use of the Faraday part. Options here given, we have them as 1.08 Faraday. Then option B, 3.30 Faraday. Option C, 1.67 Faraday. Option D, 1.80 Faraday. That is why I'll be using this part instead of this direct quantity of electricity. There are some questions given to you. This is what you will use instead of this. Suppose in the options given to us, there is nothing like F in each of those options given, right? Then this is the value we could have used already. Therefore, I can now say you cross multiply. This will go here. This gram will cancel. The quantity of electricity in terms of Faraday numbers that can do that will be 1 times 180, which is 1 times 180. You're going to divide it by 108. I'll be 108. Because you know when you cross multiply, you now divide by the quotient of what you are looking for. So our Q is equal to 180 divided by 108. 180 over 108. And that gave 1.66. So let's say this times this divided by 108. All right. So that gave 1.6666, which is approximately 1.67. 1.67 Faraday. Remember, you are using 1F times this, all over this. So the quantity of electricity I will deposit 180 gram mass of silver is 1.67. And from the question, from the option provided, the correct answer is 1.67 Farad, which is option C. Now, like I said, you could have used this formula directly. Let me write the option first. Option C is correct. Alternatively, you don't want to go through all these protocols of writing the half-cell reaction equation or the cathode and stuff like that. You can go directly by using this formula. Mass deposited is equal to, the mass deposited is equal to quantity of electricity times relative atomic mass of that substance, then divided by number of Faradays. Divided by what? Number of Faradays. This N here is number of Faradays. This N is what? Number of Faraday. The number of what? Let me put it in word. Number of Faraday. And Faraday. And you know that the number of Faraday that is required for any electrolysis process is equal to the valency of that metal. Like for silver, it's +1. If it is copper, it's going to be +2. If it is aluminium, it's +3. All right, so you take note of that. Now, looking at this, they gave us the mass deposited. This M here is mass deposited. Let me indicate. Mass deposited. That's what this M is. So from this question, we are looking for this number of Faraday. Right? Now, we are looking for this quantity of electricity. So I could just do mass deposited. What's the value? The mass deposited from the question is 180. Equal to what quantity of electricity is required, we don't know. And based on the option we are meant to solve in terms of Faraday, times relative atomic mass of silver, which is 180, divided by number of Faraday. For silver, you need 1 Faraday. 1 Faraday, right? Then from here, you cross multiply and divide by 108. So quantity of electricity will give us 1 Faraday times 180 and then divided by 108. If you look at this and you look at this, you see that you got the same thing. If you divide, you get 1.67 Faradays. Now, if in the option, we're not given the option in terms of Faraday, let's assume we are given the quantity of electricity in terms of Coulomb. In terms of Coulomb, what you will do is simple. Multiply this 1.67 by a Faraday is 96,500. So if you multiply 1.67 by 96,000, 1.67 times 96,500. Now the Coulomb value is 161,155 Coulomb. So 161,155 Coulomb is also equivalent to 1.67 Faraday. Take note of that. So you say this and this, they are the same. And we are done with this particular question. You can copy it out or screenshot as fast as you can so that we'll move on to the next question. Amarachi Godwin, so why did you not use 96,500 to multiply? I think I just explained that a moment ago. Maybe the question came before the explanation. The reason I wouldn't do that is because of the options provided. The options provided, they did not use the Faraday value in terms of quantity of electricity. They didn't use the Coulomb value. Are you getting me right? That's why each of the option had FFF attached to it, like I said. So you solve using this Faraday instead of converting to the unit of Coulomb, be the unit of quantity of electricity, which is Coulomb. So you don't need it because of the options provided. All right, we are moving on to the next question. That should be question number what? I think this is question number 4. So we should be going to question number 5. Question 5. So we are going to dictate this time around so we can be fast. Let's see the questions of answer. Question 1, question 2, question 3, question 4. Then I'm moving on to question 5. Group 9. You guys did not even number these accordingly. There are some you numbered, there are others you did not number. I don't know what the challenge is. I don't know what the problem is. You guys should learn to be doing things accordingly. Please. Life itself is meant to be orderly. So whatever you're doing, you should do it in orderly nature. Please. All right, we are moving on to the next question, question number 5. And the question reads, please pay attention, it's not calculation, so pay attention. Which of the following statements is correct during the electrolysis of a caustic soda solution using platinum electrodes? Which of the following is correct during the electrolysis of a caustic soda solution? Caustic soda is concentrated sodium hydroxide. So the question is telling us which of the following statements is correct during the electrolysis of a caustic soda, a concentrated sodium hydroxide solution using platinum electrodes. That is to say, the anode and the cathode are both platinum electrodes. Option A, oxygen gas is given off at the cathode. Option B, hydrogen gas is given off at the anode. Option C, sodium metal is deposited at the anode. Option D, sodium metal is deposited at the cathode. Option E, alkalinity at the cathode increases. For one thing I'm very sure of is that option C and option D, they are off. They are off. When you are using platinum electrode, there's something you want to take note of. There is this summary chart I dropped for you guys. All right, GMAETS for the ones lesson student, Jam and White lesson student. There was this chart I dropped for you guys that analyzed all these things. And there was something I told you in our physical class, right? Last chemistry physical class in the lesson. I told you that it seems like the use of platinum usually initiates the use of platinum electrode. That's one thing I've observed. That once you're electrolyzing any solution, any electrolyte, and you're using platinum electrode, that guy seems to allow gases to be deposited on it. Are you following? So I think the correct option will be between option A and B, where we have the gases. But the question now is which will be deposited at the anode and at the cathode. And it's simple. At the cathode, hydrogen will be deposited there. and at the anode, oxygen will be deposited. That's the correct answer to this question. So we look at it once again. The options provided. Oxygen gas is given off at the cathode. That is wrong. Oxygen cannot even go to the cathode because the cathode is negatively charged for electrolytic cell. During electrolysis, cathode is negatively charged. Oxygen is a negative valence gas or element. Are you following, right? So if oxygen, the valence is negative, there is no way it can migrate to the cathode, which already is negative. Negative will repel. So what happens is that oxygen will go to the anode, which is positive, while hydrogen will go to the cathode, which is negative. You can check that chart that I dropped for you guys, think about 2-3 weeks ago. And we also analyzed that chart in our last chemistry physical class. I taught you how you make use of it. Are you following? Yeah, so that's the correct answer, that hydrogen is deposited or hydrogen is given off at the cathode. But then, let us still look at this because I have oxygen gas is given off at the cathode. I'm saying it's not true. This is not funny. Then option B, hydrogen gas is given off at the anode. Hydrogen cannot go to the anode. Hydrogen cannot go to the anode. The anode is positively charged. The anode is positively charged for electrolytic cell. Hydrogen is positive, so hydrogen cannot go there. It's not done, right? The sodium is not deposited at any of the electrodes. So option C and D are also off. Alkalinity at the cathode increases. Alkalinity at the cathode increases. We are left with that option, no, guys. Option E. Alkalinity at the cathode what? Increases. And I guess that will be the answer. Yeah, because the solution of sodium hydroxide has been electrolyzed. Are you following, right? The final solution that will be left when hydrogen migrates and is deposited at the cathode, oxygen migrates and is deposited at the anode. What will be left as a solution there will be an alkaline solution. Will be what? An alkaline solution. Option A is not the correct answer. I told you the reason. Oxygen cannot go to the cathode. Oxygen goes to the negative. Oxygen goes to the anode instead, which is positive. And then hydrogen goes to the cathode, which is negative, because hydrogen is positively charged. So option A is not correct. B is not correct because it said otherwise. Option C and D, they are not correct because C said that sodium is deposited at the anode. That is not possible. Sodium does not even have any place to be deposited on any of the electrode in this electrolysis. So we are left with option E. Alkalinity at the cathode increases, and of course that is what I am going for as the answer. Option E. Alkalinity increases. Alkalinity increases. So that is it. I believe that if you check through that chart, likely you should see, you will find out that the solution's alkalinity will increase. All right, I think we've spent time on this just to give clear explanation to it. Let us move on to question number 6. Question 6. Again, not a calculation question. I'm going to dictate it so you follow through. Which of the following processes take place during electrolysis? Which of the following processes takes place during electrolysis? Option A. Positive ions are discharged at the anode by gaining sufficient electrons to become neutral. In fact, for saying that positive ions are discharged at the anode, that is wrong already. You already mentioned positive ions. Anode is positive electrode in electrolytic cell. So there is no way positive ions can migrate to the anode. Like I explained in question number 5, positive ions move to the cathode, which is negative electrode, and negative ions move to the anode, which is positive electrode. So option A is off. Option B, negative ions are discharged at the anode by gaining sufficient electron to become neutral. Negative ions are discharged at the anode. Yes, we know they are discharged at the anode. Then by gaining sufficient electrons to become neutral. That one I don't really think. I don't really know, because the negative ions, do they go to gain sufficient electrons? Negative ions already have electrons because those guys are negatively charged. And the concept of negatively charged means that they have excess electrons. So we'll still go there and pick electrons again. We'll come back to that option B. Let's keep it once again. Move on to option C. Positive ions are discharged at the anode, but leave that one. Positive ions cannot be discharged at the anode. I've explained that. Option D. Negative ions are discharged at the anode. Yes, negative ions, they go to the anode because anode is positive electrode. Negative ion migrates there by losing sufficient electron to become neutral. That is the correct thing, I feel. And of course, not just that I feel, that's the correct thing. Negative ions during electrolysis, they will migrate to the anode. The anode is positively charged, so the anode will attract the negative ions. Now, these negative ions, they have excess electrons. So they will go to the anode and discharge and deposit that electrons. The electrons will now move, will go to the solution, and then migrate to the cathode, where the positive ions that now goes to the cathode will now pick the electrons deposited by the anion from the anode. And you can replay this again and again. So this is just the idea. Negative ions, because they are negative, they have excess electron. They will go to the anode of the electrolytic cell. When they go to the anode, which is positive terminal, they will drop the electrons there. They will drop the electrons there. What will the electrons do? The electrons will now migrate to the cathode. The electrons will migrate to the what? Cathode. Remember, we define anode as the terminal through which current enters the electrolyte. And we also define it as the terminal through which electrons leave. I mentioned that from the outset of this class, in the background introduction to this topic, to this class. So the electrons that are deposited at the anode, they will migrate, they will move from the anode because electrons always leave the solution through the anode. They will now migrate to the cathode. When they go to the cathode, the positive ions called cations that will now go to the cathode because the cathode is negatively charged. The positive ions, cations, they need electrons because they have lost the electrons already. They will now migrate to the cathode and pick the electrons that have been discharged at that cathode, those electrons that came from the anode. So that's just the secret, the stuff, what happens in the solution. All right, so I've just given you the full idea of what this is, and that is why the correct option here is option D. Negative ions are discharged at the anode by losing sufficient electrons to become neutral. And I told you what happens to the electrons that they discharge there. So question number 6, option D. Option D is the correct option. We say negative ions are discharged at the anode. Let me write it. Negative ions. Negative ions are discharged at the anode by losing sufficient electrons. By losing sufficient electrons to become neutral. All right, let's move on to question number 8. Question number 7, rather. But before we move on to that, please take note. The same way negative ions will go to the anode to lose electrons. That is the same way positive ions will go to the cathode to pick electrons. I hope you are together, right? As I move on to the next question. Yeah, Ebere, that's correct. The answer is D. And it seems like you are the only one who got the correct answer to this. Ebere Ufikaru, right? That's interesting. And you see, for this, you are going to gain an extra of 200 unit airtime. I think you are among the people who got 500 unit airtime from the physics class. I just found out, I had to check the camera, and I found out that you already dropped option D here. And of others that attempted, you alone got the correct answer. So you're going to get additional 200 units worth of airtime. Remember, those that, I mentioned are going to be gifted this airtime. Don't forget to drop your number on WhatsApp. Send the number, a message to me on this line. Tomorrow, I'm going to send it tomorrow morning. Yeah, it can't happen this night. It can't happen this night. Tomorrow, I'll send it to you. You'll get it. Okay, so have that in mind. Question number 7. Question number 7 reads, where are we? You see, this group 9, because you refuse to number this correctly. See what you've done. I just hope those of you that would take white, you won't go and do this trash. You're answering questions, you don't number it. Please, you guys should know how to do things in order. Know how to do things in order. All these little stuffs, they are penalizable. Question number 7. Copper sulfate solution was electrolyzed using the apparatus shown above. It did not show us the apparatus here, group 9. It did not show us the apparatus. Yes, I understand that you cannot type apparatus because it's like a diagram. But this is what you should have done. These are questions people could have asked that day when I was giving the instruction in the class, in the physical class. But I remember I was talking and you people were talking. And I warned you guys, if I decide to penalize you people tomorrow now, I wonder what would happen. There is a diagram linked to a question. By the time you guys have put this question together and send it to our general group, you are meant to snap that particular diagram, forward it to that general group, and then below it, you type diagram to question so and so. Now, there's no way I can answer this question because I don't even know the diagram. It's not here. So take notes. So we're going to leave this question, but I'll just read it out anyway so everybody gets the idea of what this question is all about. Copper sulfate solution was electrolyzed using the apparatus shown above, which I am not seeing. Which of the following changes are observed? Option A, the bulb lights and copper is deposited at both electrodes. B, the bulb lights and copper is deposited at the anode and disappears from the cathode. That is what I am suspecting, this option. Because although I can't see any diagram here, you can check, can look at it. I don't know if you can see this clearly. This is the question we're analyzing. This is the question we're analyzing, this one. There is no diagram above there. But you know, experience matters. Experience matters. Good experience. High level of experience. I am thinking that this is electrolysis of copper 2 tetrasulfate 6 using an electrolytic cell with the following cathodes, with the following electrodes. The anode would be copper, tin copper, yeah, and then the cathode will also be copper. Then in that case, what usually happens at the anode, copper will be at the cathode, copper will be deposited. And then, of course, I think that would lead to lighting up because current will flow. Then at the anode, copper will dissolve at the anode. Copper will dissolve at the anode. That's what I'm thinking of, which made me, when I read out option B, I feel like that is the answer. The bulb light and copper is deposited at the cathode and oxygen liberated at the anode. Well, if the anode is platinum, then likely the correct option will be C. So it depends on the diagram. Because in the electrolysis of copper 2 tetrasulfate 6, we can use 2 different electrolytic cells. There is one we make use of, copper electrode, copper anode, copper cathode. That is the one that copper will dissolve at the anode, and copper again will be deposited as copper metal at the cathode. But then there is this one you use copper, think copper cathode, and platinum anode. In that case, copper will be deposited, I guess, at the cathode, and then oxygen will be deposited at the anode. I've told you guys something, I think in one of the questions, that platinum electrode usually attract gases. So depending on the diagram anyway, depending on the diagram referenced, the correct option can be B or C. D said the bulb light and copper is deposited at the anode and disappears from the copper is deposited at the cathode and disappears from the anode. Option D option B, please. Option B as in boy. Let's go back to that. I misread that thing. The bulb lights and copper is deposited at the anode and disappears from the cathode. That is not true. That is wrong. If you listen to my interpretation, I said earlier that copper is deposited at the cathode and disappears at the anode. Because there it's going to dissolve. At the anode, copper is going to dissolve. If they're using copper electrode, are you following, right? So that B is even completely off. It is C and D likely that would be the answer depending on the diagram. If the copper sulfate electrolyzed in the diagram, assuming it is copper electrode used, that is anode copper, cathode copper, then copper will be deposited at the cathode as copper metal. Then at the anode, copper will dissolve. Dissolving means it will disappear, which agrees with option D here. Then option C, if the electrode used are copper cathode and platinum anode, copper will be deposited at the cathode and oxygen will be deposited at the platinum anode, which goes with option C. So group 9, you have to drop the diagram to this question. Drop it. I'm giving you between now and tomorrow throughout. So let's say 24 hours. I will emphasize it in our physical class tomorrow as we take on physics, I guess. Yeah. As we take on physics, I'm going to remind you people before tomorrow, Tuesday ends. Make sure you drop the diagram to this question. Okay, now that is it. Option E, the bulb lights but no additional changes are observed. I don't think that's the option. Let's move on to the next question. So let me use incomplete. Incomplete information. Question number 8. The leader of group 9. I don't know if you are connected to this class, but in any case, anybody in group 9 in the GMAETS 41's group 9 physical class, physical jam and wire class, take notes. Take the information to your group. I will penalize you guys if you don't drop this diagram, right? If you penalize, don't drop it within the next 24 hours. All right, question number 8. We are approaching the end of this, right? So we are moving. Okay, we still have more. That's interesting. We have so much more. We are wasting time on this. In the electrolysis of dilute sulfuric acid using platinum electrodes, the product obtained at the anode and cathode are, in the electrolysis of dilute sulfuric acid using platinum electrodes, the product obtained at the anode and cathode are, no time to waste there, anode is hydrogen gas, cathode, right? Cathode rather is hydrogen gas, anode is oxygen gas. Let's move on. If you electrolyze tetrosulfate 6, right? Dilute tetrosulfate 6, that is sulfuric acid, using platinum electrodes. Hydrogen gas will migrate to the cathode, oxygen gas will go to the anode. So according to the question, the products obtained at the anode and cathode are oxygen at anode, hydrogen at cathode, which goes from here as option C. So I will indicate here, option C is the correct answer. Oxygen at anode, hydrogen at cathode. We move on to question number 9. Question 9. Okay, all these ones are stuff you can answer through, right? You can answer them. Question 9. Which of the following statements is correct during the electrolysis of a caustic soda solution using platinum electrode? We've answered this question in one other way, right? Which of the following statements is correct during the electrolysis of a caustic soda solution using platinum electrode? Remember, platinum will always welcome hydrogen, oxygen. So here we have option A. Oxygen gas is given off at the cathode. No. B, hydrogen gas is given off at the anode. No. C, sodium metal is deposited at the anode. No. D, sodium metal is deposited at the cathode. No. E, alkalinity at the cathode increases. That's the correct answer. I've talked about that before. What is meant? That's the next question. This one has been answered the same as question 5. So I don't know what you guys did. The same as question 5. Group 9, you people have looked for my trouble, you know. And I don't know why. You know, I have my principles. What is meant by I, anode, II, cathode, as used in electrolysis? That's question number 10. What is meant by I, anode, II, cathode, as used in electrolysis? Option A, anode is positive electrode. Cathode is negative electrode. That is the correct answer. Anode positive, cathode negative. But listen to option B. Anode is negative electrode, cathode is the positive electrode. That is wrong. This option B applies to electrochemical cell, not electrolytic cell. But the question said during electrolysis. In electrolysis, which of the following is anode and which one is cathode? No time to waste. Let's move on. The correct option is B. Sorry, the correct option is A. Option A. Option A. Anode positive. Anode positive. Then cathode negative. Negative in electrolysis. Okay, so finish up what you have on the board. You can screenshot so that I wipe it off, and we move on. We'll move on to the next question. So I want to ensure that nothing cuts off from your view. I'm wiping this part, and then we move on to question number what? Question 11 is the next to be dealt with. So what have we got in question number 11? During the electrolysis of copper-2 sulfate, between platinum electrodes, if litmus solution is added to the anode compartment, which of the following is observed? Once again, during the electrolysis of copper-2 sulfate between platinum electrodes, if litmus solution is added to the anode compartment, which of the following is observed? Option A, the litmus turns blue but no gas is evolved. Option B, the litmus turns blue and oxygen is evolved. They say at the anode, take note. Then option C, the litmus turns blue and hydrogen is evolved. Option D, the litmus turns red and oxygen is evolved. Option C, the litmus turns red and then becomes colorless. That one does not make any sense. That option E doesn't make sense. So during the electrolysis of copper-2 tetrasulfate 6 or copper-2 sulfate between platinum electrodes, if litmus solution is added to the anode compartment, which of the following is observed? So the answer to this question will be based on the resulting solution. What is going to happen there? Now, if you look at, we are told that this is the electrolysis of copper-2 tetrasulfate 6, and you are using what? Platinum electrodes. You're using platinum what? Electrodes. Maybe you're using platinum electrodes as if you are removing water from the solution, thereby making what is left kind of acidic. Making it acidic. And you know what acid solution does to litmus paper? You know what acid solution does to litmus. And the litmus, usually say, if a litmus solution is added. So let us say, we don't know the color of the litmus. That's what makes the question even tough. Yeah, tough in the sense that we're supposed to have been told the litmus that is being used. All right, so, but like I said, the solution is going to be acidic. If the solution is acidic, we expect that, okay, let's assume that you have blue litmus there. It's going to turn blue litmus to red. And this is happening at the anode. At the anode, oxygen is evolved there. Are you getting me right? At the anode, which is positive terminal, oxygen is evolved. So the correct answer is going to be D. The litmus turns red and oxygen is evolved. Question number 11. D. Litmus turns red. Litmus turns red. And oxygen is evolved. And oxygen is evolved. All right, so that is it. The next question, not funny, group 9. You guys messed up. You messed up. The next question is a repetition of that one of silver, where we are given 0.0012 grams per coulomb. The next one is that in which they say a graph of mass is plotted against quantity of electricity. So I don't know what's wrong with you guys, like what you brought out. So I'm going to jump all those ones, move to the next question, which is calculation. The next question there, which is calculation. So let us see what we've got there. You just kept repeating questions. Okay, now look at this. That's the next question we have here. During the electrolysis of a solution, of 0.01 mole of a metal, during the electrolysis of a solution, 0.01 mole of a metal M was deposited by passing a charge of 9,650 coulomb. Once again, during the electrolysis of a solution, 0.01 mole of a metal M was deposited by passing a charge of 9,650 coulomb. Determine the valency of the metal. Determine the valency of the metal. Then in brackets, 1 Faraday equal to 96,500 coulomb per mole. So here we don't know the valency of the metal. Let me use Xn plus. It's going to receive n electrons and be deposited as a metal. So this is what we expect. We're trying to find out what is going to be the what? The valency of that metal. Now let's look at what we have here. We are told that 0.01 mole of the metal was deposited when you passed 9,650 grams. Sorry, 9,650 coulomb of electricity through the solution. So from here, we are told that the mole of this guy deposited when you passed a quantity of electricity, 9,650 coulomb. When you pass this guy, it deposited 0.01 mole. It deposited 0.01 mole. Determine the valency of the metal. Determine the valency of the metal. If we want to get the valency of the metal, we can use, you can get it from the number of Faradays. Here we are told the quantity of electricity that was passed. We don't know the relative atomic mass of the metal, making the problem much more, complex. We don't know that. But I've given you a formula already. I gave you a formula. Since 9,650 coulomb of current or electricity was passed to deposit this. This is the mass deposited. But this mass deposited, it has this relationship to number. This mole rather has a relationship to number of moles. And I told you already that for problems like this, we have mass deposited to be equal to quantity of electricity times the relative atomic mass of that substance, which unfortunately in this case we are not given the relative atomic mass, then divided by number of Faradays. The number of Faradays will tell us the valency. The number of Faradays will tell us the what? Valency. But the problem, like I said, is the fact that we were not given the relative atomic mass of the substance. The relative atomic mass was not given to us. It was not given. But like I said, from here, number of Faraday, from which we will get the valency, if you make it subject of the formula, it's going to be quantity of electricity times relative atomic mass. Okay, now look at something. I have told you that number of Faradays is where you get the valency from. But if you look at the way we've been handling this, the number of Faraday is always obtained from the valency of that guy. If the valency is 1, you need 1 Faraday. If it is 2, you need 2 Faraday. If it is 3, you need 3 Faradays. That is the idea. Once again, I've not solved the question like this before. I've not. But we are going to use the knowledge of the known to deal with the unknown. I've given you this formula before. This is the formula you can use for any problem on first law of electrolysis. This is going to be Q times RAM, Q times RAM, and then divided by mass deposited. Mass deposited. This will go here, this will come here. Now, the question given to us, it gave us the number of moles. From this relative atomic mass and mass deposited, we can calculate number of moles. Yes, because number of moles is equal to number of moles is mass divided by molar mass. And the molar mass, if it is an element, it would be the relative atomic mass of that guy. Relative atomic mass. So watch. If number of moles is mass over molar mass over relative atomic mass, it means that relative atomic mass over mass, relative atomic mass going up now, mass coming down, this guy will now become 1 over n is equal to RAM all over mass, which is what we have here. RAM all over mass is equal to 1 over number of moles. So number of Faraday, which is the valency, or the valency of that metal, will now be equal to the quantity of electricity divided by number of moles, or times 1 over number of moles, because RAM all over mass deposited is equal to 1 over number of moles. So this is going to simply be number of moles. So moles or amount. So I guess, you see, we are making all this analysis for you to see. So as an example, you see a related question like this, you attack. So what I'm meant to do is simply to divide this 9,650 by this 0.01. Then whatever I get, I am going to do something to it using 96,500, because in this number of Faraday, you have times 96,500 to get that guy. So this is going to be 9650 divided by 0.01. I've shown you why I divided this by moles, number of moles. I've shown you the analysis here. So from here, we are going to get, okay, the number of Faraday to be this. If you divide this quantity here, this value, you have 9,650 divided by 0.01, and this gave 965,000. So number of Faraday will be equal to 965,000. Oh, hey, now watch. To get the valency, remember, I had always written this formula as NF. This N is the ionic charge of valency, right? So I can now say that valency times number of Faraday is equal to the total quantity given here, which is this guy is in coulomb per mole as a unit, which is going to be 96,500, right? 965,000. Therefore, the valency will now be equal to 965,000 divided by the number of Faraday equivalent, which is 96,500. 96,500. Are you following, right? This divided by number of Faradays that we obtained here. I think standard value for number of Faraday is 96,500 coulomb. So I'm going to divide this 965,000 divided by 96,500. So this gave 10. right? This gave 10. That's the value I'm obtaining here. This gave 10. And of course, I wonder why we get the valency to be this high. 965,000 divided by 96,500. So. The values provided, I guess I have issues with that. Or could we have divided, let's see, electroatomic mass, they gave us the mole. So if I make this subject to the formula, number of Faradays, there is a quantity of electricity here. So I'm saying 96,500 divided by 9,650 could have been 96,500 divided by 9,650, still going to give us that 10. So. I guess perhaps this might be 0.1, not 0.01. Who knows? It might be 0.1 that group 1, as in group 9, wanted to give to us. Let's check 96,500. Be 9,650 divided by 0.1. This gave 96,500 to be this value. Then you divide by 96,500 here. Divide by 96,500. 1. So this is actually meant to be 1. I suspect this to be 0.1 mole. Maybe group 1 in their, is it group 9 rather, in their usual manner, has given values that only them know where they got it from. So I am assuming this to be 0.1, but I wouldn't change anything here. Follow through the calculation. Now that I've gotten this number of Faradays for this, based on this 0.01 mole, divide it by the equivalent of 1 Faraday, which is 96,500, to get the valency of that guy. But like I said, there is an error here. There is an error here. I am being tempted to change this because there is no element whose valency is 10. There's no element, so I'm being tempted. Should I change it? I won't change it. I'm working based on what I have, so that I don't get confused. This is the process, right? The procedure of solving it. But I assume this to be 0.1. Let me change it for peace sake. So please take note. As you watch this, although I've dictated the question already, but this is 0.1 mole. 0.1 mole. 0.1. That is what will make sense. That is what will make sense, which will remove 1 0 from there. Yeah, 0.1. So you divide this, and you're going to get the valency to be plus 1. It's all right. So we are done with this particular question, and I think that is it. We still have further questions here, like 4 of them, but I'm going to just solve them, right, in a normal video. I think we've spent much time. This is 10:23, almost 10:30 now. So what we've treated here so far, I think it's enough to carry us through. Like I said, make sure you're subscribed to this channel. Make sure you always visit this channel. Visit the GMAETS41's channel. Slide through to the playlist. And whenever I release any video, whether it is live or maybe a pre-recorded video, you will get the update. Remember to turn on the notification bell. Like I've said, there are still like 4 calculation questions here, but those ones are simple questions. They are straightforward than these ones we've met. If a current of 2 ampere flows for 30 minutes during the electrolysis of molten sodium chloride, calculate the mass of sodium deposited. So it's a simple question. For that particular one, you can just use, anyway, let me wipe this. I'll just show you that. Then, like I said, I wouldn't solve the remaining 3 questions. But just tell you that those ones are simpler than what we've done so far, right? I know calculation questions are simple. If a current of 2 ampere, before I move on, for this guy, the correct option is A. Because we have the valencies option A, 1, B, 2, C, 3, and D, 4. All right, the last question, please. If a current of 2 ampere flows for 30 minutes during the electrolysis of molten sodium chloride, calculate the mass of sodium deposited. Now in bracket, they gave us molar mass of sodium, which is 23. They gave us 1 Faraday is 96,500 coulomb per mole. So it's simple. I don't even need to do anything. Sodium, the valency is +1. So take note so I will know how many Faraday is required. We need 96,500 coulomb. So this is equivalent to 1 Faraday, which is 96,500 coulomb. Are you following, right? So we are asked to calculate the mass deposited. They gave us current. Let me bring out the data. Given current is 2 ampere. They gave us time. Time is 30 minutes. Convert that minutes to second, which is 30 times 60. 30 times 60 will give us 1,800 seconds. And then they gave us the molar mass of sodium. Molar mass of sodium, which is equal to 23 grams per mole. So if you can say this, we are done already, right? We are done already. I'm sorry. Maybe I'll check the video later. If this part did not show up, then I'll still do justice to it in the pre-recorded video lesson like I told you guys I'm going to. So this is much we are taking from our class today, and I hope that you learned something from this class. Electrolysis is actually a simple one also. Be seeing you tomorrow as we look at another subject. I'll drop the information about it before the time in the evening. Take care of yourself and do have a lovely night rest. I think network is really not our friend this evening. All right. So I'm sorry, the network interfered, right? Network interfered terribly, and I don't know where you stopped, but we are done already. We are done already. I just found out that a network just connected, right? The network had just come back, but all the same, you can go through what is on the board. Can go through it. Simple. For sodium, I've given you the formula already, so you substitute and then you solve. I hope that this explanation showed for you to get it, because we are done with the question. The remaining 2 simple questions we are going to, I'm just going to do some brief work on it. Network was really not friendly from here today, but we thank God that we are able to do some good stuffs. All right, we're able to do some good stuff, and I'd like you guys to take good care of yourself. Have a wonderful night rest. That said, tomorrow we move again. There is no time. Always remember to take your studies seriously.